Very much, and thank you all for joining us again. Today's webinar centers on a common problem faced by engineers and contractors and owners who are dealing with an exasperating situation or situations that are associated with improper boiler venting. The causes are varied, leading to an array of damaging and expensive consequences, which if the causes were better understood up front, they could be avoided. So during this webinar today, we're going to, for time purposes, we're going to limit our discussion to forced draft, natural gas-fired commercial and industrial boilers, both condensing and the non-condensing type. We're going to first look at the problems associated with poor venting systems and then discuss the major causes. So problems first, then the causes associated with these problems. We'll then get into the proper design considerations and conclude with Chuck solving two specific exhausting problem scenarios. And they, of course, would incorporate some of the design principles that I'll be discussing before he gets into the scenarios. So beginning with the problems caused by improper boiler exhaust venting, when we consider improperly engineered new or existing systems which have been changed or added to without considering the increased mass flow and the temperature associated with these changes, we're going to run into problems such as you see here. So these are the common problems: efficiency loss, boiler damage, increased boiler maintenance, and so on. And it's because we're not taking certain things into consideration when we are laying this breeching and stack system out. So if we take a look at the first three, efficiency loss, boiler damage, and increased boiler maintenance, let's just concentrate on those first. When we say that we've got efficiency loss, and I keep driving this home in our seminars, we've got to remember that a boiler will consume 4 times its initial cost in fuel consumption a year. That kind of puts things in perspective. So you may ask, well, okay, that's fine, Steve, but how does boiler venting, breeching, and stack sizing affect efficiency? And that's a good question. So let's look at that. Here you see a boiler. We took a picture of this. This boiler was in excellent condition. As a matter of fact, about a month or two before this boiler was opened, and you see what you see here, it was tuned up. Proper fuel-air ratio, everything was fine. You can take a look at the rear door here. There's no signs of cracking or anything else. This boiler was well maintained, and it was tuned up. What they did is they added another boiler downstream of it. They ducted it into the breeching before it hit the stack, and this caused a lot of back pressure because we had increased mass flow in that breeching. It caused a huge pressure drop, resistance to flow. That impacted the fuel-air ratio, and we started sooting up. Now, you can't see it very well here in this slide, but what happened is we overheated that pressure vessel, and those tubes began to push away from the weld and crack. So it led to a pressure vessel repair that you see here. Because of that soot being deposited on the heat transfer surfaces, it impeded the heat transfer, and as a result, the pressure vessel overheated, the tubes extended, and the welds cracked. Now, another thing that we have to concern ourselves with is condensation that will build up in the breeching or the stack that can impact not just the breeching and stack itself, if it's not of the proper material, but also the boiler itself. If you take a look here, you see the vent outlet, which is welded to the shell extension of this fire tube boiler. The hot gases come out and go up through this vent. If we get into a condensing situation, this is carbon steel. It's going to begin to corrode, not just the vent, but the boiler extension itself. So here you see a good shot of that boiler vent coming out of the shell extension right here. You can see it's carbon steel and how it could definitely corrode with condensation building up and dripping down. Now, the next next three things that we want to look at is damage, breaching, and stacks, production downtime, and increased operating costs. These are the problems that we're facing now with a poorly designed stack and breeching arrangement. If we use the wrong material for the stack itself, this can lead to some serious problems, not just in terms of repair, but downtime. I can't tell you the number of instances that I've seen carbon steel breeching and stack being used for boilers that get into very, very close condensing situations and have some real problems as a result. So when that's got to be replaced, various sections have to be replaced. Obviously, the boiler is down, and if you don't have standby, your production also is impeded. So downtime becomes a real problem, and it can be directly associated with stacks. Another problem that can lead to downtime is as you increase that pressure in the stack and breeching, you've got that pressure now being imposed upon the burner itself, we get into pilot problems. We also get into situations where we have flameouts if that restriction is large enough. So those are other problems that can lead to not just maintenance issues, but expensive downtime as well. So if we take a look, and we're in a very, very competitive situation in this country today. It's a world economy that we deal in. Manufacturers, industrials have to control their costs. And if you take a look at the total spend as far as operating expenses in a plant are concerned, you can see that one of the biggest contributors to cost, of course, is fuel. The thing that we have to keep in mind that a boiler system is like a body. And if any one of the organs in the body is compromised in any way, the body itself, of course, does not function properly. The same with a boiler system. The stack and breeching are just as much a part of this system as the burner is, as the controls are. It's extremely important. So it impacts fuel. It also impacts services in and out, the supplies, the repairs and improvements. All of these cost areas can be impacted by improper stack and breeching design. So what are the causes of the major problems? Well, there's a number of causes. And the first thing that we're going to be looking at today would be poor design, undersized for the duty, boilers have been added, too much resistance. So we'll be looking at these three right here. Boilers added, undersized for the duty, and poor design. Let's look at those first. Here's a good example of a breeching arrangement that has certainly not been laid out properly. You can see that we've got an appliance here, and then we're coming across with a common breeching, picking up a couple of units, and not enlarging that breeching as we increase the mass flow. So that is a telltale sign right there that we're going to have some significant problems as far as overpressure is concerned. Now here's another situation where you can see we've got a carbon steel stack here, but that's not really the issue. The issue is that I've got a boiler here that was put in, and then another one was added. And if you look closely, we do not have any expanders here. There's no expander before it goes into the vertical stack itself. Now, in this particular case, that's not a problem. And the reason is because the vertical stack to which this breeching is connected and these two boilers are being vented into is tall enough to overcome that resistance. So we still have enough negative to be able to vent the products of combustion. What about environmental variances, external conditions and external conditions? Those two, just before wrong material. Here you see a situation where we've got a tall stack. As a matter of fact, those two boilers that I just showed you, before that are being ducted commonly into that breeching and then into the stack. This is the stack right here. Now, should it have a cap on it? Here's the problem. We've got a number of conditions that will impact the amount of draft, the pressure density differential within the stack itself. Things like ambient temperature, relative humidity, wind velocities, and barometric pressure. So the design engineer, when he's looking at laying out, or she's looking at laying out a breeching and stack arrangement, they take these things into consideration to make sure that we've got 0 to slightly negative at the vent stubs of these boilers to be able to adequately vent the products of combustion. Here you see, if we put a stack, here's another problem. This would be an external condition. Let's say that we were coming through this ceiling right here, or this roof right here, with a stack where the arrow is pointing. Notice this column next to it. This could induce a downdraft. So that would have to be taken into consideration. Either we would take that stack up above this column, a couple of stories higher, or we would have to have certainly a cap on top of it. But then remember that as soon as we put a cap on top of a stack, we've now introduced another restriction. We've got a 90-degree bend now that those products of combustion, which is nothing more than a fluid, have to bend, and of course when they turn to go out underneath that cap, that's another resistance, and will add linear feet to the overall calculation. So what about the wrong material? That's another common cause of problems, maintenance problems, downtime, and so on. When we look at the venting material for boilers, we can break them into 4 categories. We've got category 1, which would be atmospheric, really an atmospheric type condition where you've got a total negative within the stack and breeching all the time, and it's non-condensing. Then we've got category 2, which could be pressurized but also non-condensing. Category 3 would be positive vent pressure but non-condensing. So many fire tube and water tube boilers would fall under that category, especially when you're talking about process steam. They're going to, if you've got a forced draft boiler, burner combination, it is going to be venting into a category 3 vent arrangement, if you will. It'll be non-condensing but pressurized because it's got a forced draft burner. If we get into condensing boilers, hot water, hydronic heating, that's going to be a category 4 because they are designed to condense. So the 2 categories that we are going to be concentrating on today for time reasons will be the category 3 and category 4. So pressurized, non-condensing, category 3, and category 4, which will be condensing and pressurized, positive vent. Now, looking at some examples of those, we see we have a category 3, which would be this particular boiler, a flex tube water tube boiler, flex water tube boiler. Got a power burner. We're talking category 3 because it is positive pressure and non-condensing. This boiler right here is a hot water boiler, but it is near condensing. In other words, it's about probably operating around 87, 88% fuel to water efficiency. So you're going to have a certain amount of condensing in that particular situation. So we would go with a category 4 material because of that condensing possibility and the possibility of corrosion if we don't have stainless steel material that would be coming in contact with that flue gas. And here's another category 4. This is a full condensing boiler that operates with category 4 material all the time. So I'm saying if you get into a near condensing situation, you want to go with category 4, as well as a condensing boiler, of course, has to go with category 4. Now, the other thing is certification. With these materials, it's highly recommended by the industry, not just Cleaver-Brooks, that the material be UL certified. So with the certification in the States, it's UL 1738, and in Canada, it's ULCS-636. And as you can see in the bold letters here, in the bold type, gas temperatures not exceeding 550 degrees with a maximum rated positive pressure of 15 inches of water column. That would fall under the category UL 1738 and ULCS 636 in Canada. And this is what the label would look like on the material, on the breeching sections and the stack sections. You would find a label that looks very, very similar to this. Now, as far as the materials are concerned, if we're looking at the materials of construction, you see that there's stainless steel, either 301 or 304, 316 or 316L, which is low carbon. And also there's an aluminized steel type 430. The aluminized steel is on the outside. So we've got a double wall. We've got the stainless steel comprised of the stainless steel material that you see here. And then we've got the outer wall, which is an aluminized steel. In between, we have either 1 or 2 inches of insulation. That can either be air, or mineral fiber wool, or ceramic fiber. Air, of course, would give you the least amount of R factor, if you will, in terms of insulating value. But of course, it's less expensive, and it's lighter. So the engineer would be selecting, given the particular situation that he's designing for, would be selecting the proper material. So, with this as a bit of background, what are some of the design variables one has to consider when laying out a proper boiler exhaust system? So these now are the design variables. If we start from the very top here, this is what the engineer has to take into consideration before they start the overall design and calculation. What about the local codes? I mentioned the insulating material. A lot of times local codes will dictate under what circumstances certain materials have to be used. For instance, I'm concerned about maybe a combustible wall. I might be running a stack or a breeching through a combustible wall, have to take it through a chase possibly. So the local codes become very, very important for the engineer to make some of the initial assumptions or initial criteria through which he then is going to lay out the entire design. The next thing we have to look at, of course, is the type of fuel. We mentioned that we're going to limit our discussion today on natural gas, but it could be number 2 oil, it could be number 6 oil, for goodness sakes. But natural gas, of course, is the prevalent fuel, and of course, as you know, it's got a lot of methane in it. And it's primarily a lot of hydrogen. So it's going to create a lot of condensate. And that condensate is going to occur at a temperature of about 130 or 135 degrees. So you could have a boiler that's operating at 100 pounds pressure, which is 338 degrees, but you still could get into a situation if that breeching and stack has not been properly designed, where even though you're coming out of that stack at, say, close to 400 degrees, by the time it gets to the stack, it could be down to dew point. And that becomes very, very important. And of course, if you've got an oil fuel, that dew point's even higher. You're talking 235, 240 degrees with number 2 oil. So that becomes a huge consideration, the type of fuel I'll be burning. What's the flue gas temperature, as I mentioned? Becomes important. What about the appliance category? So now that I've got all of this, I know the type of fuel, I know what the flue gas temperature is going to be, now I can begin to make decisions on the category that I'm going to be using as far as my stack material is concerned. Is it category 3 or will it be category 4? If I'm near condensing, I'll go with category 4. What about the altitude? What's the altitude going to do for me? Well, as we go up in elevation, of course, the air becomes what? Less dense, right? So this impacts my pressure density differential and the ability of my stack to pull the proper negative, if you will, and be able to vent properly. So altitude is a huge concern as well. If I'm at sea level, I don't worry about it. But if I'm in Denver, it's a major concern. Then what about the flue gas velocity? And of course, this has to do with temperature and mass flow. So how many boilers do I have connected to that breeching, and how much mass flow do I have? What's the diameter of the breeching? What is the velocity going to be? This then, of course, also gets, when I start knowing what the velocity and mass flow are, and then the velocity, I can begin to calculate the resistance to flow, the pressure drop. The other thing is the summer versus winter. You know, I've got situations where the boiler might draft very, or the stack and breeching will draft well, let's say in the wintertime, but in the summertime, when I lose my temperature delta T, it doesn't do very well, and the relative humidity goes up. So I got to take these things into consideration too. What about seismic and wind loads? Stack and breeching diameter, height, and length. Now I begin to calculate that. And then I have to also, when I'm doing that and I'm laying it out, I have to think about other things like, where are the flow restrictions? Do I have T's and elbows? What about Y's and dampers and reducers? These will all affect the resistance to flow and increase the pressure drop. And speaking about Y's, well, here's a good example. I'm coming out of this boiler and coming into the stack. But notice I don't bullhead into it. I don't just T into it. I use a Y to sweep the products of combustion into the stack. Try to impede the resistance to flow as much as I possibly can. Now here's another example of a Y connection, but in this particular case I've got a condensing boiler. I'm coming from the boiler into my common breeching, but I do it with a Y, so I sweep into it, I don't impede flow, and then go into an insulated chase between the walls and up through the roof and outside. And of course, as you can, this particular stack and breeching material is a category 4, full condensing. Now, I would be remiss if I didn't mention this at this particular time. There are differences out there in terms of design, various manufacturers. We all build basically the same thing, but the way the stack and breeching go together, there are differences there. There are some people that use just a flange, where you take the two sections together, and the flanges then butt together, you seal and band them. In this particular case, it's a male-female connection. Why does that help? It helps in the overall assembly. It reduces the amount of time it takes to put these sections together. So when you're choosing these materials, look at the manufacturer and how they go together. How are these stack and breeching sections designed? Are they butted flanges, or are they male-female connections, which in fact could save some labor out there in the field? Now we get into some of these draft conditions that vary. In this particular case, what I have is I've got a high stack, and that's all. I'm not concerning myself with anything other than a stack draft that might vary based on the season. In the wintertime, I may have more draft than I do in the summertime. And so what I've got is a mechanical damper here that I can set, so I know that when I modulate that burner from low to high fire, I've got just the amount of resistance. Either I increase the resistance or I decrease the resistance to be able to handle that particular draft situation throughout the firing rate during that season. I might have to adjust it in the winter, or I may have to adjust it again in the summer, but it's just a mechanical damper. So sometimes those are used. Other times where the variation could be quite extreme, and it's impacted by velocity outside, wind velocities, downdrafts, varying temperatures, barometric pressures, and so on, where I really get a lot of variance, then I may want to go with an automatic stack damper that you see right here that's tied into a pressure sensor. That then is measuring the amount of negative or positive within that stack and then adjusting automatically the damper to suit that variance. Now, in some cases, especially where I've got a retrofit and I've added a couple of boilers, I've kept the existing breeching, I don't have money to add any more to it, I know I can make this thing work if I put in an induced draft fan. And those induced draft fans can either be mounted in the vertical stack, as you see here, or they could be mounted in the horizontal and thereby overcome the resistance to flow mechanically, driving those products of combustion to the stack and up and out. So that might be another thing. The other thing that we run into often with stack and breeching are low-budget situations where a boiler has been added and they want to use the existing stack. And this could be a total retrofit. Maybe it was an old coal-fired plant. The boiler came out and new boilers went in. The budget, as I said, is a problem. They want to use the existing chimney. Well, we're going to have problems with that existing chimney if we don't take some precautionary action here, and that would be with a stack liner. So rather than going with a separate stack, as you see here on the left, we're going to use that existing chimney and do what we can with it. So we're going to run a liner in there, so we will keep it from the products of combustion from condensing and degrading the masonry, and still vent properly as though we were taking those products of combustion into a brand new stack. So when everything is all said and done, you've got that liner coming through the chimney and up and out to the atmosphere as you see here. Now for those in the United States or in the UL, it's UL, or in the US I should say, it's UL 1777 would be the UL certification number, and in Canada it's ULC S635 for those liner materials. And of course we're looking at, in those particular situations that are certified by UL, we're looking at temperatures that would not exceed 570 degrees. So, with that then, as a bit of background, I thought it would be a good idea at this point to have my associate here, Chuck Zinda, take us through a couple of scenarios and you know, what he goes through when he's properly engineering and designing a stack and breeching layout. So, Chuck?
All right, thanks, Steve. The first project that we'll look at is a new multi-story manufacturing facility that requires the installation of two forced draft fire boilers in the mechanical room, as depicted in this engineer's drawing that was submitted for bid. These boilers are firing natural gas, operating at 100 psi, with a projected stack temperature of 360 degrees Fahrenheit. The boilers will operate in a fully modulating lead lag setup with one or both boilers firing at the same time depending on the production load. Looking at the elevation view in the middle of the drawing, you'll see that the engineer has shown one boiler connecting to the chimney with a 90-degree T, and the second boiler entering the chimney just above the first boiler connection with a 45-degree Y connection. Our factory engineer runs a draft calculation on all quote requests that we receive, which we'll see in the next slide. Here I've highlighted that in the draft calculation, the 90-degree T connection that was designed, that was shown in the design engineer's drawing, which gives us an available draft. Down here at the bottom, we show the available draft calculated at a positive 0.006 inches water column. Now, it's a pretty small amount above zero, but still our calculation is showing that as too small of a diameter. So we want to aid in the evacuation of the exhaust gases. So we're going to size the breeching and chimney to achieve a slight negative draft at the boiler exhaust outlet. In this case, we have a slight positive. So we're going to take a look at this again and see what else we can come up with. A positive draft available could cause a buildup of back pressure at the entrance to the chimney, causing burner combustion issues, resulting in potential boiler heat transfer issues that Steve had previously discussed. Now, using the draft calculation that we just performed as a starting point, we're going to consider changing that 90-degree T in the original engineer's layout to a 45-degree Y that we're showing here at the bottom. Running a new calculation based on that, you'll notice that we've taken out the 90-degree T connection, we've replaced that with a 45-degree T connection, and the resulting draft calculation shows us with that negative 0.053 inches water column, which is what we're looking for, and our draft calculation says okay. So that was just all we needed to do on this particular application, and we came up with a solution to that problem. This 45-degree Y offers a more laminar flow to the exhaust gas, whether one or both of boilers are operating. In our next application, the project we're looking at, which just came into us recently, is a boiler replacement in an existing facility. Two older non-condensing steel boilers are being replaced with two condensing boilers utilizing the existing chimney chase. The last boiler in line is 30 feet from the chimney with a straight breeching run combining both boilers. These are heating boilers firing natural gas with a low return water temperature, resulting in a lower stack temperature of approximately 200 degrees Fahrenheit. As shown in a previous slide by Steve, a common misperception is to size the breeching diameter the same size as the boiler gas outlet, the boiler exhaust gas outlet, for the entire run from both boilers to the chimney. We're going to take a look at a draft calculation using that single size diameter breeching. Now, I've highlighted a spot here in the draft calc where we did not include an increaser, which we would normally consider, but we're going to go with the example we talked about as using a same size diameter breeching, which is a 12-inch for the boiler exhaust fitting, showing us that we're going to have an available draft of a positive 0.116 inches water column. Again, the calculation is telling us it's too small of a diameter. This confirms Steve's earlier discussions about not considering the increase in mass flow when adding a second boiler to the exhaust system, resulting in back pressure increases and poor burner operation, including pilot failures for the downstream boiler. The condensing style boilers are more susceptible to these pressure fluctuations. If we consider an increaser in the breeching, as shown here in this elevation view, at the point of entry of the second boiler exhaust, we have now increased the cross-sectional area of the breeching to handle that increase in gas volume. Now let's take a look at that revised draft calculation. Here I've highlighted the fact that we've put an increaser into our calculations, into the flue or breeching run. And our flue diameter is 18 inches with both boilers, as shown here, resulting in an available draft of negative 0.070 inches water column, which is what we're looking for, which gives us the okay sign that we've got an acceptable draft for these boilers to operate. Steve, these are just two examples of the design issues that our factory engineers see on a daily basis. They review all of the exhaust system requests that we receive for proper design, and they perform draft calculations to ensure that the boiler and exhaust system operates efficiently.
Okay, well, thank you, Chuck, very much. I appreciate that. Let's, in summary, what are the takeaways from what we've talked about so far this afternoon? The main point I would like to get across, or points I'd like to get across, are exactly what are here on the screen right now, that an exhaust system is an integral part of the overall boiler operating system, if you will. It's just as important as anything else on that boiler or anything else in that boiler room. It's part of the system. And of course, improper exhausting can lead to expensive results, not just additional fuel, but maintenance, downtime, and so on. So keeping these things in mind when a boiler is added or when new boilers are being installed, another one's being, let's say, replaced, like I mentioned before, an old coal-fired plant being replaced with gas or oil-fired boilers, the exhausting, the venting of these new boilers becomes very, very important, especially if the existing stack or chimney is being used. Ventilation air. Very, very important that ventilation air be part of this. And let me just give you an example. In the very beginning, we have to make sure that the boiler room itself has got enough ventilation air. And what we use as a rule of thumb is 10 CFM per boiler horsepower. 8 CFM for combustion and 2 for ventilation. Not to keep you comfortable, but to make sure that that room does not go negative, okay? Or does not go positive, I should say. We want to make sure that we do not go positive in the boiler room itself. Okay, now, the other problem that we have is, so we've got 10 CFM per boiler horsepower. Now, how does that equate to the proper cross-sectional area for ventilation? If you take a 300 horsepower boiler, if we add 10 CFM per boiler horsepower, that's 3,000, right? So we've got a total of 3,000 cubic feet. Divide that, if you've got a ceiling that is 7 feet or lower, let's say 7 feet, you divide that by 250. By 250, and that will give you the cross-sectional area that you need to properly vent that boiler room. If the ceiling is higher than 7 feet, then you divide by 500. So you take that 3,000 divided by 500, that would give you the cross-sectional area for ventilation and combustion air. So these are the things. One must understand the variables before laying out a stack and breeching system. Obviously, the proper material selection based on the category becomes important. We went through those today. Category, we stress category 3 and 4, but of course you may get involved with categories 1 and 2 as well, with atmospheric gas-fired appliances, or that could, become positive in that breeching or stack, in which case it would be a category 2. So, and then the last thing, of course, stack and breeching designs vary, and one must be aware of those systems which not only provide the solution for the conditions, but installation savings as well. So there's differences out there relative to how these stack materials go together that can certainly impact the overall installation cost. So I think those are the takeaways. If we take a look at those 6 bullets, if you've gotten nothing more out of this webinar today than taking those back with you, I think you've accomplished a lot, and we have as well. So with that, I'll open it up to questions.
Thank you, Steve, and thank you, Chuck, very much. At this time, if you would like to ask Steve or Chuck a question, please present it in the Q&A tool of the WebEx control panel. And if you would, make sure that it is that you select all panelists so that we're in different areas and we can each see what the question is and we can get it answered appropriately. While we are waiting for those questions to come in, I just want to reiterate that today's presentation will be archived and located on the Cleaver-Brooks website. You can see today's presentation in its full audio and video. And you can also download a PDF of the slide presentation. Today's presentation as well as the ones that we've had in previous months. Next month, our topic will be the right boiler for the application. We'll look at the different types of applications, and then given the application, what are the issues that you might encounter during the decision-making process, and then what boiler types best address those issues. So if you'd like a little additional information on next month's topic, be sure to visit the website at cleaverbrooks.com/webinars. And with that, we do have a couple of questions that are already in, so I'm going to just let you volley it back and forth, Chuck and Steve, as you see fit. One of the first questions we received earlier in the presentation was, what types of problems arise with common stacks serving multiple, or common stacks serving multiple boilers? that is sized for full installed capacity? Is there a recommended minimum turn down as a % of installed boiler capacity to ensure proper draft at all times?
Well, let me take a whack at that first, Chuck, if I might. If you've got a number of boilers connected to a common breeching and stack, you're going to have to make sure that it has been designed to be able to handle the maximum. So it would be the maximum turn down. In other words, each one of those is going to have to be sized as though they were all operating at 100% capacity. Otherwise, you're going to get into problems. In that particular situation, you could also get into an oversized condition where maybe those dampers that we talked about, the automatic damper, would be sensing the excessive negative pull within the breeching and stack, and as a result would begin to pinch off and increase the resistance. Because, you know, with these, what you're looking at is either zero draft at the vent stub or slightly negative. That's the ideal condition that Chuck was actually driving at when he was going through those two scenarios. Now, there are some boiler manufacturers that can, based on the boiler burner package, you can tolerate plus or minus a quarter inch, plus or minus a half inch, but that depends upon the manufacturer. So it'd be a good idea for the engineer who's ever involved in laying out that stack and breeching arrangement that they understand what boiler is being connected to it. They contact the manufacturer and ask whether or not they can, under what conditions they can operate without adversely affecting combustion.
Okay, thanks, Steve. And if there's information that is needed in addition to that, there is a number at the end of the PowerPoint. There's a slide for more for additional information, so you can feel free to call Chuck Zinda, email him, or give him a phone call. Next question we have: do all stacks have to be double wall? And kind of along with that, is the exterior on double wall stacks available in one of the stainless steel grades?
Say that again, please. Could you repeat that?
Yes.
The material.
Do all stacks have to be double wall? And along with that, is the exterior on double wall stacks available in one of the stainless steel grades?
Oh, they don't have to be double wall. It's a kind of a protection issue, insulating issue. You know, if it's going through a wall or a roof section. We've provided many single wall stacks. As far as stainless, it is available for the exterior wall, for the outer wall in 304, 316, a number of different materials. We've selected aluminized steel as kind of a standard. It's a cost issue. Mostly it's a cost issue, but we've provided aluminized steel on the interior section of the stack and stainless steel on the outer, the exterior that's exposed to the atmosphere.
Okay, next question. You mentioned suiting of the boiler heat transfer surfaces causing efficiency loss. How much suit to equal a 1% loss in efficiency?
Well, I can handle that one, Chuck. I think if you're looking at, let's say, anywhere from a 1/16 of an inch to an 1/8 of an inch of soot on the heat transfer surface of the boiler, you're going to see some elevated temperatures. You're going to see the temperature of that stack rise quite predominantly. And to exactly, you know, what is going to equate to is it going to go up 40 degrees from the benchmark? Maybe. In which case, it's a 1% loss. So you're going to see a dramatic increase when you see soot at, let's say, a 1/16 of an inch to an 1/8 of an inch. You're going to see a dramatic increase in temperature, and for every 40 degrees over the benchmark, you're going to lose a % of fuel efficiency.
All right, next question. Okay, there's understanding of the need for adequate combustion air, but how do you calculate the free area? How do you handle cold air temperatures entering the boiler room?
Well, as I mentioned before, as far as the free area is concerned, you use 10 CFM per boiler horsepower, and depending upon the height of the ceiling in the boiler room itself, 7 feet, you would divide by 250. If it's over 7 feet, you'd divide by 500, and that would give you the cross-sectional area. You would then divide that in half and put 1/2 of that opening on one side of the boiler room and 1/2 on the other, 7 feet or lower. Now, if it's cold temperatures, and you've got this this open area, let's say it's louvered, you can have dampers put on there that are tied into the control circuit of the boiler or boilers, and would only power open under those conditions when the boilers are firing, and then would drive shut when the boilers are down. Of course, when the boilers are firing, it's going to warm up that boiler room considerably. And normally, if you're talking temperatures outside of 10, 15 degrees, 20 degrees, something like that, it doesn't really cause a problem. When you get into some real cold temperatures, say northern Canada, or even here in the States in the lower 48 or 50, you're going to get into certain situations where it's really, really cold. In that case, you're going to have to probably think about air heaters or electric resistance, something to heat that air before it comes in.
Okay, Steve, what about, how does sealed combustion factor into the exhaust calculations?
Do you want to take that, Chuck? Sealed combustion. In sealed combustion, of course, what you've got is you've got air being ducted into the burner itself, and then you've got your vent going out in a separate system. Many times that ducted air, as far as secondary air for combustion, it's PVC pipe. Do you want to comment on that at all?
Not sure how I can answer that one. The question is what about the combustion air ducting, you mean? How does it affect the operation?
Well, yeah, I mean, you've got to calculate that as well.
That one, I'm not sure how to answer that one in particular.
I mean, are you going through the calculations on the air coming in, the secondary air coming in for combustion? Obviously, there's resistance to flow there, so you're going to have to calculate the diameter of that. Of the
combustion air duct, so that we provide adequate air.
Right.
Correct. Yeah.
And then, obviously, the way the vent would be calculated would be the same as though it was not sealed combustion. I'm talking now about the vent to the outside.
Correct.
So yes, to answer the questioner's question, definitely the calculations for ducting the secondary air supply for combustion would be very similar to that which is used for the venting of the combustion air after post-combustion.
Okay, and as I stated earlier, if there's additional information needed, feel free to email those questions to Chuck, and we can distribute them through the company to the best person to be able to answer those questions for you. Next question, when would a mechanical damper be added to an exhaust system?
Well, we'd add the mechanical damper to control the gas flow, to give us the correct, hold on a second here, to give us the correct draft. If we have too much draft, we're going to want a mechanical damper to control that, to control the flow and the draft out of there. So we can put them in. You can put either a mechanical open-close and then be able to adjust, or you can put an automatic draft damper in to control it to the precise, a little more precise, especially if you have more than one boiler involved. we do that quite often. Each application has to be looked at individually.
Okay. In the scenarios that you gave, Chuck, let's see, both examples showed an open chimney top. The question is, what happens when it rains?
Well, when it rains, what we do in these particular cases, we didn't have a cover on it. The inner wall is stainless steel, so corrosion won't be a major factor in that. But both systems that we show also have drain tees installed at the bottom of the stack for drainage of any condensate or rain that may collect in the stack.
All right, and let's see, we have time for just a couple more questions. Can you recommend a good draft inducer manufacturer?
Well, I can take that. Yes, a couple that I've come across throughout the years. Exhausto makes an excellent induced draft fan. And most of the Exhaustos that I've seen mount in the vertical, oftentimes right on top of the stack. The other company that I've had good experience with is Turndown, Turnlund, Turndown. And I've seen those in the horizontal breeching, but I think they also make a vertical appliance.
Okay. Next question. With a forced draft boiler burner combination, how do you know what is the correct pressure within the stack, plus or minus, for the boiler to operate efficiently?
That's an excellent question. And that's kind of what gets back to what I was mentioning before, but what I would suggest that the person do that's getting involved with the stack and breeching layout and design, contact that boiler manufacturer, find out what they can live with that particular model and a burner boiler combination. Like for instance with Cleaver-Brooks and our fire tube boilers, we can you know, withstand plus or minus, depending upon the model, plus or minus anywhere from 1/4 inch to 1/2 inch of variance in stack pressure without adversely affecting the burner and combustion. There might be other people out there that say, look, I've got to have 0 and that's it. 0 at the vent stub. If you give me any variation, I'm going to have problems. Well, that's fine. Then we just design around it. And if that means that we've got to go to an induced draft fan, or we've got to do something to enlarge the breeching, or do something with the resistance in terms of avoiding the T's and going into Y-type connections, whatever we can do in the most economical way to give that boiler what it needs in terms of draft is what we have to do.
Steve, this question comes in. Would you suggest adding a motorized damper at the exit of each boiler?
No, I think that not just as a carte blanche statement, no. I think that the situation has to dictate the expense. Don't do anything you don't have to do. If you get into a situation where you've got a lot of variances, as I mentioned before, caused by downdrafts or wind velocities or ambient temperatures, whatever it might be, then it may be prudent to take that step and invest in a induced draft system or an automatic dampering system or whatever. But if you've got pretty good assurance that the conditions are fairly stable, then it's just a matter of properly calculating the breeching and stack diameters and lengths in order to be able to you know, accommodate the proper draft. My counsel is don't spend anything you don't have to.
Okay, I know that we have a good many questions that have not been answered as of yet. Don't fret, we have a copy of the questions, and we will be sure that we get you an answer or contact you directly, either by the information that you submitted via email or telephone call. So go ahead, and if you still like to submit a question, go ahead and do that. And what we'll do is we'll make sure that it is answered and gotten back to you in a timely fashion. Again, look for next month's topic on our website. webpage, cleaverbrooks.com/webinars. Get a copy of today's presentation, voice and audio, plus a copy of a PDF that you can use. If you did not indicate that you wanted a certificate of attendance, please do so through the survey that is automatically sent to you as you exit out of WebEx, and we'll be sure that you get your certificate. At this time, we are only giving certificates for the live events and not for any archived events or events that are, if you should go on there and view at a later date. You should receive those certificates between 2 to 5 business days, but if you don't receive it then there's an email address that you'll be able to contact us. I appreciate everybody's time. Thank you, Chuck. Thank you, Steve, for a good webinar, and we will see you guys next month on the 29th, I believe, is when we are giving the next presentation. And any other closing comments, Steve?
No, that's it. Thank you all again for joining us. We really appreciate doing this, and we appreciate your attendance.
All right. Thank you so much. Have a great day.
You too.